Speed, power, momentum. High-speed rail engineering focuses on minimizing friction. On the other hand, an average 2,500-ton freight train has enormous momentum and needs huge traction power to get moving. After covering vast distances at high speed, the train arrives smoothly and comes to a stop. Now, let's look at the engineering behind how passenger and freight trains stop. We will talk about air brakes, magnetic brakes, regenerative braking, retarders, and others. Do you hear that hissing sound? That's air being released. A train can't brake from a single point. Braking has to be distributed along the entire train, through these lines. Before explaining the process, let's understand what each symbol in this diagram represents. This is the locomotive's air compressor, and it supplies compressed air to the entire train's braking system. This is the driver's brake controller, which controls brake pipe pressure. From the locomotive, the brake pipe runs along the entire train. This single pipe, located at the edge of the rolling stock, connects to the next wagon and continues along the train. This is the locomotive's air brake distributor, which distributes air braking based on brake air pressure. Auxiliary reservoir stores compressed air and supplies to the brake cylinder when the air brake distributor is activated. Brake cylinder converts compressed air pressure into mechanical force to apply the brake shoes to the wheel. This is what happens when applied brake on train. And now let's check why this happened on a train. When the driver applies braking, air is released from the brake pipe and the distributor senses the pressure drop. This pressure drop triggers the distributor to open the path from the auxiliary reservoir, allowing stored air to flow into the brake cylinder, where it pushes the pistons and applies the brakes. And that's the engineering secret behind the sound you hear when a train stops. But air brakes alone are not enough and efficient for high-speed trains, so they use different braking mechanisms. When a high-speed train is moving fast, it carries a huge amount of kinetic energy. Instead of wasting this energy as heat, modern trains use it to slow themselves down. As braking begins, the traction motors switch into generators and convert speed into electrical energy. Only at lower speeds do air and disc brakes step in to bring the train to a smooth and controlled stop. This process, called regenerative braking, does most of work at high speeds. This is an example of disc brake on train. A magnetic track brake uses powerful magnets to clamp directly onto the rail, allowing the train to stop quickly in emergencies. This capability is critical for emergency braking, especially on trams, metros, and others, where short stopping distances are vital. However, it is not suitable for long and heavy trains, because the strong friction on the track would be too harsh and unsafe. But not all brakes means to stop a moving train. Some brakes are designed for specific situations, such as shunting and speed controlling at hump yard. Here, wagons are pushed over a small hill and then rolled down by gravity. Their speed isn't controlled by drivers, but with help of retarders. Track-mounted retarders gently squeeze the wheels to control speed and prevent hard impact. In a shunting yard, workers place rail skids on the track to catch moving wagons, using friction to bring them to a smooth, controlled stop exactly where needed. Finally, the parking brake is applied to mechanically secure the wagon in place once it has come to a complete stop. Overall, the main purpose of all braking system is to control movement and maximize safety. Feel free to ask any question. Thanks you for watching. I hope you found this video useful.